Section 4.6 Nozzles and Diffusers. We are going to evaluate open systems, flow going in and out of the control volume. And we'll take a look at common steady flow devices. The steady flow devices mean that any thermodynamic property will have a fixed values at the given locations and will not change with time. A steady flow device includes nozzle, diffuser, turbine, compressor, pump, heat exchanger, and throttling device. Now we will study all these steady flow devices. In thermodynamic systems, there is a need to either increase or decrease the velocity of a fluid. So nozzles and diffusers are used to change the velocity of a flowing fluid. A nozzle is a device for increasing the velocity of a fluid in the direction of the flow. And the purpose of nozzles is to increase the velocity or kinetic energy of a fluid stream. And this is possible by decreasing the cross-sectional area of the flow in the nozzle. So as the pressure of the fluid decreases, velocity increases. If we compare the velocity at location 1 and location 2, velocity 2 is greater than velocity 1. And this is because the area at location 2 is smaller than the area in location 1. The pressure of the energy of the fluid is converted to the kinetic energy. And if we compare the pressure at location 1 and 2, the pressure at location 1 is greater than the pressure in location 2. So the pressure energy of the fluid is converted to the kinetic energy. On the contrary to this, a diffuser is a device that decreases the velocity of a fluid in the direction of the flow. And this is possible by increasing cross-sectional area of the flow in the diffuser. So as pressure increases, the velocity of the fluid decreases. So compare the velocity at location 1 and 2. V1 is greater than V2. Compare the pressure at location 1 and 2. P2 is greater than P1. So the kinetic energy of the fluid is converted to the pressure energy. So it is the opposite of a nozzle. So nozzles and diffusers work in opposite ways. Let's consider an open system. There's a single inlet, position 1, and single outlet, position 2. Enthalpy at the inlet H1, pressure P1, velocity V1. Enthalpy at the outlet H2, pressure P2, velocity V2. And the elevation of inlet is Z1. Elevations of the outlet Z2. So the specific kinetic energy at the inlet is half of V1 squared. The specific kinetic energy at the outlet is half of V2 squared. The specific potential energy at the inlet is GZ1. The specific potential energy at the outlet GZ2. The change in specific kinetic energy between the inlet and outlet is half of V1 squared minus V2 squared. The change in potential energy between the inlet and outlet is Z1 minus Z2. The change in enthalpy between the inlet and outlet is H1 minus H2. So we can take the energy balance on the device based on this idea. The analysis of nozzles and diffusers are quite similar. The first law of thermodynamics for open system may be expressed as this. So this is the general form of energy balance equations. The equation is expressed in a rate form. It includes different forms of energy: heat, work, enthalpy, kinetic energy, potential energy. So Q dot is the rate of heat transfer. The unit is kilojoule per second or watt. W dot is the rate of work or power, also kilojoule per second or watt. M dot is the mass flow rate through the device, kilogram per second. The subscript CV on the work is the rate of work that is done by the system or control volume. So it may be shaft work or electrical work. And the term with the subscript 1 indicates the energy entering the system, and the term with the subscript 2 indicates the energy leaving the system. Q is assumed to be into the system. W is assumed to be out of the system. The equation can be simplified by making appropriate assumptions. So if no work is involved within the nozzles and diffusers, it drops out. If there is no potential energy change between the inlet and outlet of the device, it drops out. How about kinetic energy? So there is a significant change in kinetic energy. V2 is greater than V1 for nozzles. V1 is greater than V2 for diffuser. So we will keep the change in kinetic energy. If the nozzles and diffusers are well insulated, there will be no heat transfer between the device and the surroundings, and the process is called adiabatic process. So Q dot drops out. This is the simplified energy balance equations. Example 4.3. A steam entered a converging diverging nozzle operating at steady state with P1, 40 bar. So pressure is given 40 bar, temperature T1, 400 degrees Celsius, and the velocity 10 meter per second. The steam flow through the nozzles with negligible heat transfer and no significant change in potential energy. So no heat transfer. So Q dot is 0 and no significant change in potential energy. So potential energy is also 0. At the exit, pressure P2 15 bar and the velocity is 665 meter per second. The mass flow rate is 2 kilogram per second. Determine the exit area of the nozzle in meters squared. So first, let's see what we know from the problem statements. At the inlet, pressure, temperature, velocity are given. Steam entered the nozzle, so we know that it's a superheated phase. At the exit, pressure and the velocity is given. So we need one additional property to fix the states. According to the conservation of mass flow rate at the inlet is equal to the mass flow rate at the outlet. So we can write mass flow rate at the inlet 2 kg per second. And mass flow rate at the outlet is also 2 kg per second. And we want to determine the area at the exit. And the mass flow rate can be expressed density at the exit times velocity at the exit times area at the exit. Or this is equals to volumetric flow rate divided by specific volume at the exit. And we want to solve it for the area at the exit, which is equals to mass flow rate specific volumes over velocity at the exit. So we know the mass flow rates and the velocity at the axis. So once we fix the state at the exit, we can determine the specific volume at the exit. So we are going to determine one more property at the axis, and we are going to use the energy balance to determine the unknown. And we are going to apply the energy balance on the nozzle. Since the nozzle is well insulated, Q dot drops out. And there is no work associated with the nozzles, so W dot drops out. And assuming the elevation of the inlet and outlet is negligibly small, so the potential energy change between the inlet and outlet drops out. So we can simplify the energy balance equations. From these energy balance equations, we can solve it for H2. At the inlet, pressure is 40 bar and the temperature is 400 degrees Celsius. And the enthalpy at the inlet is here. And the velocity at the inlet and outlets are given. And here we need to be careful to make the unit consistent. The unit of enthalpy is kilojoule per kilogram. And the unit of specific kinetic energy is meter squared per second squared. So we need to unify the units first. So enthalpy at the exit is determined. So at the exits, we know the pressure and enthalpy, two independent intensive properties. So we can fix the states. So what we want to determine is the V2, specific volume at the exit. So see table 8.4. So this is the tables at 15 bar, and H2 is between these two numbers. And we can interpolate to calculate V2. So we can determine the area at the exit. 4.7 turbines. There are different types of turbines: gas turbine, steam turbine, and hydraulic turbine. It is found in power plants and aircraft engines. So it is a device that harnesses a gas or liquid to produce useful work. For example, the shaft of a turbine rotates a generator to produce electrical energy. Fluid passes through the turbine and rotates the shaft by expanding a gas from a higher pressure to a lower pressure. Work is done by the fluid. The energy difference between the fluid entering the turbine and the fluid leaving the turbine is the work produced by the turbine. Note that the turbines produce shaft work. Turbines are work-producing devices. It is also considered a steady flow device, so it operates at steady-state conditions. The work produced by a turbine will be smaller if there is heat loss to the surroundings. So turbines are built to minimize the heat loss and increase the efficiency. Consider a turbine with one inlet and one outlet. The energy balance equation can be written in general form. And if the change in kinetic energy of flowing metal is negligible, the kinetic energy terms drops out. If the change in potential energy of flowing metal is negligible, potential energy terms drops out. If the turbine is well insulated, so there is no heat transfer with the surrounding, Q dot drops out. The simplified energy balance shows that the work produced by a turbine is the enthalpy change from the inlet and outlet of the turbine. Enthalpy is the sum of internal energy and flow work. So to have high enthalpy, fluid enters the turbines at high pressure and high temperature. To have low enthalpy at the exit, fluid leaves the turbines at low pressure and low temperature. So it will produce high W work. Example 4.4. Steam enters a turbine operating at steady state with a mass flow rate of 4,600 kg per hour. The turbine develops a power output of 1000 kW. At the inlet, the pressure is 60 bar, temperature is 400 degrees Celsius, velocity is 10 meters per second. So since we know the pressure and temperature at the inlet, we can fix the state, and the work output is given. At the exit, pressure is 0.1 bar, and the quality is 0.9. And the velocity is 30 meters per second. So pressure and the quality is given at the exit, so we can also fix the state. It's a saturated liquid vapor mixture since quality is given. Calculate the rate of heat transfer between the turbine and surrounding in kilowatt. So we can fix the state at the inlet and outlet, and we are going to apply the energy balance on the turbine to determine the Q. Since steam entered the turbine, we know that it's in the superheated phase. At the exit, we have a saturated mixture. So this is the general forms of energy balance equations. The elevation difference between the inlet and outlet is small, so the potential energy drops out. We want to solve it for Q dot. We know the work produced by the turbine and the velocity at the inlet and outlet. And we can fix the state at the inlet and outlet, so we can determine the Q dot. At the inlet, pressure is 60 bar, temperature 400 degrees Celsius. So H1 is here. And at the exit, quality is given. We know that it's saturated liquid vapor mixture. At 0.1 bar, enthalpy for the saturated liquid, enthalpy for the saturated vapors are shown here. So the enthalpy at the exit can be determined. We also need to make sure that we unify the units. So we solved it for Q dot. The rate of heat transfer is negative 62.3 kilowatt. So negative sign indicates that heat is removed out of the turbine. 4.8 Compressor and pumps. Compressors and pumps are devices that increase pressure of fluids. Their function is the same, to increase the pressure of a fluid. So compressor is used to increase the pressure of a gas, and pump is used to increase the pressure of a liquid. So fluid enters the device at low pressure, and work is supplied to rotate the shaft in the compressors and pumps. They require work input. So compressors and pumps are work-consuming devices. On the contrary, turbines are work-producing devices. As fluid passes through the device, the blades compress the fluid. So the fluid leaves the device at high pressure. The energy balance in general form is shown here. If the change in kinetic energy of flowing matter is negligible, kinetic energy drops out. If the change in potential energy of flowing matter is negligible, potential energy drops out. If the compressors or pumps are well insulated, there is no heat transfer with the surrounding. So Q dot drops out. And since the compressors and pumps are work-consuming devices, W should be negative. Example 4.5. Air enters a compressor operating at steady state at a pressure of 1 bar and a temperature of 290 Kelvin and a velocity of 6 meters per second through an inlet with an area of 0.1 meters squared. So the pressure, temperature, velocity, and area at the inlet are given. So we can fix the state at the inlet. So at the exit, pressure, temperature, velocities are given. So we can fix the state at the exit. Heat transfer from the compressor to its surroundings occur at a rate of 180 kJ per minute. So in these questions, the compressor is not well insulated, so there is a heat loss to the surrounding. Employing the ideal gas model, calculate the power input to the compressor in kilowatt. So air is the working fluid, and we assume air is an ideal gas. It satisfied ideal gas law. We are going to apply the energy balance equations for open systems. And we are going to assume that the potential energy difference between the inlet and outlet is negligible. And we want to determine how much work is required to compress the air at the given conditions. So we solve it for work. So we know the heat loss to the surroundings. We fix the state at the inlet and outlet, so we can determine enthalpy at the inlet and outlet. The velocity at the inlet and outlets are given. The only thing is unknown here is m dot, mass flow rate. Mass flow rate can be determined by volumetric flow rate divided by the specific volume at the inlet. Since air is considered an ideal gas, we use ideal gas law to determine the specific volume. Heat loss to the surrounding is kilojoule per minute, and we are going to convert it to kilojoule per second. So multiply by, and enthalpy at state 1, 290 Kelvin. This is H1. Recall that enthalpy is only function of temperature for ideal gases. Enthalpy at state 2 at 450 Kelvin. Enthalpy is here. Since compressor is a work-consuming device, W is negative. If W is positive for compressor, then something wrong with your calculations. So check your calculation again.